Welcome, this is Coach Dorf. We're going to continue our discussion about calculus. Today we're going to talk about L'Hopital's rule. Before I get into L'Hopital's rule, let me show you a little puzzle. All right, the question is, what is 1 plus 2 plus 4 plus 8 plus 16 plus ... What does that equal? All right, I'm going to claim that that all equals -1. All right, that may surprise you because you would think 1 plus 2 plus 4 plus 8 plus 16 plus ... would equal infinity, but I'm gonna show you that it equals -1. All right, to do this, I'm gonna call x equal to the sum. So x is 1 plus 2 plus 4 plus 8 plus 16 plus ... And now I'm going to take this equation I have, and I'm going to multiply both sides by 2. So 2 times x is going to give me 2x. 2 times the right side will give me 2 plus 4 plus 8 plus 16 plus ... And now I'm going to subtract the top one from the bottom one. So on the left side, I'll get 2x minus x. And on the right one, I'll get 2 plus 4 plus 8 plus 16 plus ... minus 1 plus 2 plus 4 plus 8 plus 16 plus ... So on the left side, I get x. And on the right side, I'll write it as 2 plus 4 plus 8 plus 16, getting rid of the parentheses. And then when I, for the second parentheses, I'll have to distribute that negative. So I get -1, -2, -4, -8, -16, minus ... And then I can cancel some things out on the right side. The 2 and the -2 cancels out. The 4, -4, 8, -8, 16, -16, and the plus ... with the minus ... So then I have x equals -1. But what was x? X was 1 plus 2 plus 4 plus 8 plus 16 plus ... And so that equals -1. That was my claim. What's up here? Well, really what's happening here is 2x is really going to be going to infinity, and x is going to infinity. So what we've done is 2x minus x is infinity minus infinity. And this infinity minus infinity is known as an indeterminate form. Let me get this right here. Okay, indeterminate form. And it means that in its present form, we don't have enough information to figure out what its value is. So infinity minus infinity, we can't do that. We have to find another way to evaluate it. We just can't go infinity minus infinity. All right. So that's what we need to talk about first. What are indeterminate forms? So we have some of the most common ones here are 0 over 0 and infinity over infinity. That will happen when you have a fraction. Another common one is to go infinity times 0. What is infinity times 0? We have something really, really large and something really close to 0. Is it going to be really, really large? So is it going to be infinity? Or is it going to be really close to 0? Or is it going to be something in between? We need more information. We need to rewrite this in a different form so that we can evaluate what it actually is. All right. Some more indeterminate forms are infinity to the 0 power, right? Because if I have something really large and I put it to the 0 power, well, if I have something really large and I put it to any power, you would think it'd be large. But if I have something to the 0 power, you would think it would be 1. So is it something really large like infinity, or is it 1, or is it something in between? Same thing with 0 to the 0 and also 1 to the infinity. Is 1 to infinity? 1 to any power is 1. All right, like 1 squared is 1, 1 cubed is 1, 1 to the 4th is 1. But something to a really large power like infinity, would that be infinity? Okay, and a fourth type we have is this infinity minus infinity that we talked about at the very beginning. All of these are indeterminate forms, and so we're going to need to, in order to evaluate indeterminate forms, we're going to have to do some more work. We can't just say that infinity minus infinity is 0. All right, let me give you some concrete examples of indeterminate forms. So these are, again, some indeterminate forms. expressed as limits. And that's what we're going to be concentrating on today, indeterminate forms expressed as limits. So we could have something like the limit as x goes to 0 of 2 to the x minus 1 all over x. All right, so why is this an indeterminate form? Because if I do my direct substitution, right, we'll do direct substitution over here, I'm going to have 2 to the 0 minus 1 over 0. And what is that going to be? Let me rewrite this here. 2 to the 0 is 1, so we get 1 minus 1 over 0, or 0 over 0. That's an indeterminate form to have 0 over 0. All right, let me give you another example here. Well, suppose I have the limit as x is going to infinity of x times e to the negative x. What does that equal? Well, as x is going to infinity, x is going to be infinity times, because we have a times right here, so there's going to be a times here. And what happens to e to the negative x? Well, remember, if I have my graph here, this will be the graph of e to the x. So y equals e to the x looks like this. The graph of y equals negative e to the x looks like this. That's the graph of y equals e to the negative x. And in this case, what's the limit as x goes to infinity of e to the negative x? Well, it's getting closer and closer to 0. So that limit is going to equal 0. So if I go back to the original problem I had here, we know that this part is going to go to infinity, and this part here is going to go to 0. So we have infinity times 0, and that is an indeterminate form. All right. Another example of an indeterminate form here. Let's suppose I have the limit as x goes to infinity of x to the 1 over x. All right. What's the limit as x goes to infinity of 1 over x? Well, you can think of it a couple ways. That means that the denominator is getting really, really large while the numerator is fixed. And if it's getting larger, the denominator is getting larger, then that means the whole fraction is going to get closer and closer to 0. I can also look at it in terms of a graph. Okay, the graph of 1 over x looks like this. It's a hyperbola. And as x gets larger and larger, that limit is going to get closer and closer to 0. So that limit there is going to be 0. So this original problem here has an indeterminate form, but that's not right equal here. But what's that going to equal? It's going to be looking like infinity to the 0 power, and that is an indeterminate form. Also indeterminate form. And so there are several different ways your indeterminate form can look like. Again, we have those all listed up here, are the most common ones. And we did 3 examples of types of problems. We've got this A, this B, and the C are all examples of different indeterminate forms where A is 0 over 0, B was infinity times 0, and C was infinity to the 0 power. All right, so what can I do when I have an indeterminate form here? Well, you can do a thing called L'Hopital's rule. Now, there's some controversy about how you actually say this. I don't know French. L'Hopital is a French word. I don't know how to say it. So, but what I've always heard is L'Hopital's rule, and the way that that the textbook spells it is La Hospitals. So I'll use that. Some people spell it differently, but the important part is that it's the same rule, and we can use this when we have an indeterminate form. So L'Hopital's rule says if you have an indeterminate form of 0, 0, or infinity over infinity, then your limit as x goes to a of f of x over g of x is going to equal the limit as x goes to a of the derivative of f over the derivative of g. So again, if I have this fraction form with f over g, and when I put in the limit there by direct substitution, I get 0 over 0 or infinity over infinity, then that's L'Hopital's, that's an indeterminate form. Oh, let's see, I forgot the word form here. So let's just put that in there. Okay, if you have an indeterminate form of 0 over 0 or infinity over infinity, then you take the derivative of the top, and then you take the derivative of the bottom, and you rewrite them, and you can evaluate the limit, and it will give you the same value of the original limit. Okay, notice we're not doing the quotient rule here. We're not applying the quotient rule to f over g. We're just taking the derivative of the top over the derivative of the bottom. Okay, what if I have one of these other indeterminate forms? Like what if I had, so what if we have like infinity times 0? What do I do? Well, what you're going to do is you're going to rewrite it. So you're going to rewrite the limit to get something that's going to be like f over g. All right. Or the same thing is if I have something like infinity minus infinity. So if we have, or something to a power, like we talked about some other power ones. Earlier we saw we had a power one that was infinity to the 0, or if we have infinity minus infinity. So you rewrite it to get a fraction or a rational expression of the form f over g. Okay, and we'll give some examples of that so you can see how that works. But the key idea here is that if I have a limit of f over g, and when I do direct substitution, I get 0 over 0 or infinity, then that limit is going to equal the limit of the derivative of the top over the derivative of the bottom. All right, so here's an example. Example number 1. Okay, so find the limit as x goes to infinity of 3x plus 1 over 5x minus 2. Now, this may look familiar to you because many lessons ago, we evaluated this one. We were able to figure out what this limit was. So what did we do before? Well, let's first look at what happens when I put in infinity here. What do I get in the top and what do I get in the bottom? Well, this is an indeterminate form of infinity over infinity. Now, notice, I don't usually like to write that this limit equals infinity over infinity. So I will just put a parenthesis here and write down infinity over infinity in the parentheses there, instead of saying it's equal to it. I think that's more precise, and it's a better way to write this. Okay, it's part of my preference. I just don't want to do that. So what did we do before? So before, when we had such a problem like this one, we would multiply, that we would notice that the top and the bottom have the same degree. The degree here in the numerator is 1 because we have an x to the first power, and in the denominator we have degree 1. So it's x, because it's x to the first power. So we would take the original rational expression and we'd multiply the top and bottom by 1 over x. We get 1 over x because it's degree 1, so we put 1 over x to the first power. If the top and bottom are both degree 2, it'd be 1 over x squared. Degree 3 on the top and the bottom would be 1 over x cubed, and so forth. And then what we did was we multiplied through that 1 over x, so that we got then 3 plus 1 over x in the numerator. All right, let me just demonstrate that. We're going to multiply the 1 over x times the 3x. The x's cancel out and I just get 3. And then I do the 1 over x times 1 and I get 1 over x. In the denominator, then doing the same thing, we'll get 5 minus 2 over x, because we're distributing the 1 over x to the 5x. So that gives me 5x over x, which reduces to 5. And then I get negative 2 times 1 over x, and that gives me negative 2x. And then we had a result that said, in such a case, as the limit goes to infinity, 1 over x goes to 0, and same thing, 2 over x also goes to 0. And so we ended up with the result 3/5. And that's what we did several sections ago. Okay. With L'Hopital's rule, though, we can also do this one, and it's pretty easy. I'd say very easy. Here, we've got the limit as x goes to infinity of 3x plus 1 over 5x minus 2. And we know, again, that the numerator, as x goes to infinity, as x gets really, really large, the numerator is going to get really large, so we'll say infinity. And likewise, the denominator, as x gets really large, then the denominators will get really large, so we get infinity over infinity. So my original expression, that limit, is equal to the derivative of the top over the derivative of the denominator. And when I do that, I take the derivative of the top, derivative of 3x plus 1 is 3, and the derivative of the denominator, 5x minus 2, is 5. And so I get the answer 3/5. That's really cool. That's really simple and straightforward. And I like that example a lot. Okay, so let's do a little bit more complicated example, showing this L'Hopital's rule. All right, so we're going to find the limit as x goes to 0 of 2x that quantity minus 1 over x. All right, so we first notice that that limit is, we're talking about that limit as x goes to infinity of 2x minus 1 over x. That's going to be of the form, whoops, sorry, made a mistake there. That's supposed to be that x is going to 0 here. Okay, so then I'm going to have, if I do direct substitution in the numerator, I'll have 2 to the 0 power minus 1 over 0. Let me fix that here. And then what is that? 2 to the 0 is 1, so I have 1 minus 1 over 0, which is 0 over 0, which is an indeterminate form. Okay, so before today, then we couldn't use what we had done in the previous chapters, where we had, like in example 1, where we had a degree 1 polynomial over a degree 1 polynomial, and then we could multiply through by 1 over x. We couldn't do that for this particular example, so we would be kind of stuck. But here we can now do L'Hopital's rule. So we use L'Hopital's rule, which I'm going to abbreviate as LH. So I'm going to get the limit as x goes to 0 of 2x minus 1 over x. It's going to be the same thing as the limit as x goes to 0 of the derivative of the top over the derivative of the bottom. All right, now what's the derivative of 2x? All right, that may be something that you are a little bit have forgotten, but this is a good chance to review it. The derivative of 2x is 2 to the x times the natural log of 2. And the derivative of -1 is 0. All right. And then in the denominator, we have the derivative of x, which is 1. And so the answer is, oops, I forgot my limit sign there. So let me just write that in here. So I have the limit as x goes to 0 for that. So I have my limit as x goes to 0 of 2 to the x times natural log of 2 over 1. And when I put in 2 to the x there, I'm going to get 2 to the 0 times natural log of 2, and 2 to the 0 is 1, so I get natural log of 2. And that's my answer. That's what that limit is. This original problem here, find this limit as x goes to 0 of 2 to the x minus 1 over x. It equals natural log of 2. And you get that, we got that by doing L'Hopital's rule. All right, let me give you a little bit harder example of L'Hopital's rule here. So example 3. Let's look at the limit as x goes to 0 of e to the 3x minus 1 minus 3x all over x squared. Okay, so on this one, again, if I do direct substitution here, I'm going to get x is going to 0, so I get e to the 0 power minus 1 minus 3 times 0. And in the denominator, I get 0 squared. E to the 0 is 1, so I have 1 minus 1, minus 3 times 0, which is 0 all over 0, and so I get 0 over 0. So indeterminate form here of 0 over 0. So we can do L'Hopital's rule. So by L'Hopital's rule, then we get the limit as x goes to 0 of e to the 3x minus 1 minus 3x all over x squared. And L'Hopital's rule then says, when I do this, I'm going to take the derivative of the top. All right, writing that down over the derivative of the bottom, or the denominator. Okay, so keep writing my limit signs here. Derivative of the top. What is the derivative of e to the 3x? Well, that derivative is 3e to the 3x. By the chain rule, that's what we get. And then the derivative of minus 1 is going to be 0. And then the derivative of minus 3x is going to be minus 3. All right, and then in the denominator, derivative of x squared is going to be 2x. Okay, so now we evaluate the limit. When I do that, what do I get? I'm going to get 3 times e to the 0 minus 0 minus 3 over 2 times 0. And that's all going to equal here 3 minus 3 over 0, which is 0 over 0. And so I still have an indeterminate form again. Okay, does that mean that we've failed? No, because L'Hopital's rule doesn't say I can only do this once. I can do this again and again, because this, I had my original problem. It equals the limit of the derivative that we just did by L'Hopital's rule. Okay, so if I do the derivative again, it's going to be equal, that next one's going to be equal to this first derivative I did, which will then be equal to the original problem. So we're going to use L'Hopital's rule a second time. So now I'm going to get the limit as x goes to 0, and I'm going to do the derivative of what I have here, 3x, 3 to the e to the 3x minus 3. So I'm going to take this, that's what I'm going to do for L'Hopital's rule. And then here, I'm going to take the denominator, and I'm going to get the derivative of 2x. All right, so then that's going to equal the limit. And now I'm going to take the derivative of 3e to the 3x. I bring that 3 from the 3x, the numerator from the exponent there, I bring that 3 out front, and I'm going to get 3 times 3 or 9e to the 3x. And I get a 0. In the denominator, I've got that here, derivative of that would be 2. So now when I do the evaluation of the limit, I'm going to get 9 e to the 0 minus 0 over 2, which is going to be 9 times 1 over 2, which is 9/2. And that's my answer, 9/2 there. So this demonstrates that sometimes you're going to need to do L'Hopital's rule more than once, and you can do that on a problem and get the correct answer. No problems there doing that. Okay, let's look at another example. So we've looked at examples, an easy example that was similar to what we did before. We looked at another easy example, straightforward example with a natural log. Then we looked at this one, this previous example where we had to do L'Hopital's rule twice. So here's this fourth example here. We're going to find the limit as x goes to infinity of x e to the negative x. Now we looked at this one at the very beginning, and remember that when we looked at the example of the graph of y equals e to the negative x, that limit as x goes to infinity of e to the negative x equals 0, because this here, as I go farther and farther right, it's getting closer and closer to 0 here. So this problem that we have, the limit as x goes to infinity of x e to the negative x, is going to be of the form infinity times 0, which is an indeterminate form. form. Okay, but it's not something where we have infinity over infinity or 0 over 0. So we want to rewrite this one so that we get a rational expression and that the rational expression has infinity over infinity or 0 over 0. So one way I could do that is take, I've got two terms here. I've got x and I've got e to the negative x. I can put one of those in the denominator, all right? I could do this, I could do the limit as x goes to infinity. I could keep the x in the numerator, and remember that if I have e to the negative x, that's the same thing as 1 over e to the positive x. So we're going to take this idea and plug it in here to get x over e to the x, like that. All right, so we're taking e to the negative x that's in the numerator and rewriting that as 1 over e to the x. And so we still have the x in the numerator. So then I'm going to get this, what I have here, x over e to the x. So that's equivalent to what we had before, what we started with. And now we notice, if we look at this, if x is going to infinity, this gives me infinity over infinity. That's what this is. And that's an indeterminate form. But it's an indeterminate form that's a rational expression. And so now I can apply L'Hopital's rule. So we're going to use L'Hopital's rule at this point. And so we're going to get that this is going to equal the limit as x goes to infinity of the derivative of the top over the derivative of the denominator. And what's that going to equal then? So we get the limit as x goes to infinity. The derivative of the top is 1. The derivative of e to the x is just e to the x. And then what happens to e to the x as x goes to infinity? Okay, that's going to be get really, really large. So this is going to go to infinity. And so if you got 1 over something that's really, really large, that's going to equal 0. And that's my answer for this one. We're going to get 0 there. All right, let's look at another example here. So in this example, we're going to find the limit as x goes to infinity of x to the 1 over x. So now if we look at this, if we do a direct substitution, we know that as x goes to infinity, 1 over x is going to go to 0 because you have, again, you have a fixed number, a 1 in the numerator, and you have an x in the denominator, and x is getting really, really large. So 1 over a really, really, really large number is going to 0. So this is going to have the indeterminate form of infinity to the 0 power. So let's just look at that indeterminate form a little bit. It's, I think, easy to not understand what's happening with that one. So just suppose we have this here. Okay, we're going to look at, again, x to the 1 over x. So if we're going to do something like x values and then x over 1x values. So if x is 1, then we have 1 over 1 to the 1 power, which equals 1. If x is 2, we have 2 to the 1/2 power, which is the square root of 2, which is approximately 1.41. If x is 3, we have 3 to the 1/3 power, which would be the cube root of 3, which is approximately 1.44. Okay, and we could keep doing this. What's going to happen to this result here? What happens to x to the 1 over x power as x approaches infinity? That's the question here. You might think that, well, it's going to go to 1. You might think because you have the 0 power, and anything to the 0 power you've been taught is 1, but infinity is not a number. It just means a really large number here. And so if you have a real large number to the 0 power, does it go to 1? Could it go to something else? Could it go to infinity? Could it get really, really large? All right. This is the beauty where now we can use L'Hopital's rule to actually answer this question in this particular case. Okay. So again, what we're trying to do is find, in this problem, we're trying to find the limit as x goes to infinity of x to the 1 over x power. And we saw that this was of the form infinity to the 0 power, which is an indeterminate form. So we're going to use L'Hopital's rule. But we don't have a 0 over 0 or infinity over infinity. Okay. So we need to rewrite this as a 0, as a fraction, or more precisely, as a rational expression. Okay, a ratio of something over something. All right, so remember back when we did logarithmic differentiation, we would have something like this. We'd have x to the 1 over x power, and we wanted to take the derivative. To do that, we would take the natural log of both sides so that we could bring the exponent out front, and then we had a product rule problem. So we're going to do the same thing here. So we're going to say we're going to let x or y equal, so let y equal x to the 1 over x power. All right. Then we're going to take the natural log of both sides. So then we have the natural log of y equals the natural log of x to the 1 over x. And as I mentioned, the reason you do this is because now you can bring this exponent out front so that it now looks like 1 over x times the natural log of x. Okay, so we've got that. And then we have, this tells us that the limit as x goes to infinity of the natural log of y equals the limit as x goes to infinity of 1 over x times natural log of x. All right, now do we have a rational expression? Do we have something like that when we put in the limit there by direct substitution, we get 0 over 0 or infinity over infinity? Well, not quite yet, but we can rewrite this to get that form. So rewrite the right-hand side. And so we're going to have the limit as x goes to infinity of 1 over x times natural log of x. We're going to write that as a rational expression by doing putting natural log of x in the numerator and x in the denominator. So what we've done is that this red part is equal to the green part. Okay. Now, when we do direct substitution, so notice that the limit here, if we do this, we got this limit here. If I do direct substitution, I'm going to get the natural log of x as x goes to infinity is infinity. And why is that? Because the graph of the natural log of x, remember, looks like this. There's y equals natural log of x. And as x is getting larger, the graph is getting, the y value of the graph is getting larger and larger. So that's going to be infinity over, as x gets large, we get infinity. So we have infinity over infinity. So indeterminate form. And it's an indeterminate form of 0, 0 or infinity over infinity. So that works really well. So we can use L'Hopital's rule. Use L'Hopital's rule here. And so we're going to have the limit as x goes to infinity. We go way back at the beginning. The natural log of x is equal to the limit as x goes to infinity of natural log of x over x. Yeah, so maybe I said that wrong, but let me do this again. On the left-hand side, we have the limit as x goes to infinity of the natural log of y. And you may say, well, why y doesn't have any x's in it, but y is dependent upon x. So we're going to just write it that way for now, and that we'll be able to use that. Okay, so now we use L'Hopital's rule. So by L'Hopital's rule, the right-hand side becomes the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. And so that's going to be the limit as x goes to infinity of 1 over x over 1, which is the same thing as the limit as x goes to infinity of 1 over x. And we have that same situation now where we have a 1 in the numerator, an x in the denominator, and x is going to infinity. So this is going to be 0. Now that's not my answer. Okay. This meaning 0 is not my answer. Why not? Okay. It's not my answer because this was, on the left-hand side, we had natural log of y. So natural log of y equals 0. We didn't have y, we had natural log. We want y. So how do I get y by myself? So how do we get y by itself? Well, we put what's on the left side and the right side as the exponent to e. So we can do e of natural log of y equals e to the 0. And when you do e to the natural log of y, you just get y. And on the right-hand side, you get 1. And so this is my answer, 1. 1 is my answer. So in other words, we had the limit as x goes to infinity of x to the 1 over x does equal 1 there. Okay, and that was, remember, we had the indeterminate form of infinity to 0. That was what we started with. So it did turn out to be 1 in this case. All right, one last example here. So that was example number, what did we do? Oh, I didn't label that one. That was example number 5. So now we have example number 6. Okay. And this will be the last example of a case where we don't have the 0 over 0, infinity over infinity form. So we're going to rewrite it to get it to that so that we can solve something that has the indeterminate form. So I'm going to do the limit as x goes to 0 of 1 over x minus 1 over e to the x minus 1. So, and we're approaching 0 from the right. Okay. So let's see here. If I do a direct substitution here, what happens to 1 over x? So as x approaches 0 from the right, and you may wonder, why do we have it from the right? Remember, so the first term is this 1 over x. That's this hyperbola that looks like this. And as x approaches 0 from the right, then 1 over x approaches positive infinity. Okay, if we did the limit as x approaches 0 of 1 over x, the limit doesn't exist because one of the sides goes to infinity and one goes to negative infinity. So we have to say it goes to 0 because this one is going to infinity, and this is going to negative infinity. So 1 over x goes to negative infinity as x approaches 0 from the left. But in this case, 1 over x goes to positive infinity as x approaches 0 from the right. That's why the original problem has plus infinity there. Okay, so 1 over x is going to go to positive infinity. And how about 1 over e to the x minus 1? Well, x is going to 0, so this is going to go to e to the 0 minus 1, which is 1 over 1 minus 1, which is 1 over 0, okay, which means it's approaching infinity also. So the limit as x approaches 0 from the right of 1 over x minus 1 over e to the x minus 1 is approaching infinity minus infinity. And that's an indeterminate form. Remember at the very beginning of this lesson, we talked about that if you had infinity minus infinity, we got something that looked really, really weird. And so you can't just say that infinity minus infinity is 0. So we have an indeterminate form here. So we want to rewrite 1 over x minus 1 over e to the x minus 1 as a rational expression or a fraction. Okay, so how do I do that? Get a common denominator. So I've got x for one of my denominators and e to the x minus 1. So we're going to start with that. We're going to get a common denominator, and that's going to be multiplying the two denominators together. Well, let me rewrite it this way. Okay, so I have 1 over x. I want to multiply that denominator by e to the x minus 1. So I have to multiply the numerator by that. So that's what this part is going to. And then here, I'm going to have 1 over e to the x minus 1. And I want to multiply the denominator by x. So I'm going to multiply the numerator by x. And so this part is this right here. Okay. And so then I'm going to get e to the x minus 1 over x e to the x minus 1 minus x over x e to the x minus 1 here. And so I get e to the x minus 1 minus x over x e to the x minus x. All right. In this case, I'm going to multiply through in my denominator this x part. I'm going to multiply it by both things to get what I have there. Okay, so we want the limit as x goes to 0 from the right of, again, the original problem was 1 over x minus 1 over e to the x minus 1. We've now rewritten that one. What's in the parentheses there, we've rewritten that to be e to the x minus 1 minus x over x e to the x minus x. And now if we do a substitution there where x equals 0, trying to solve the limit, we get e to the 0 minus 1 minus 0 over 0 e to the 0 minus 0. And that's going to give us 0 over 0, which is my indeterminate form. And not only is my indeterminate form, it's also an indeterminate form that we can use L'Hopital's rule on. So by L'Hopital's rule, we're going to get the limit here is going to equal the derivative of what's in the numerator over the derivative of what's in the denominator. All right, so then we have that limit as x goes to 0 from the right. In the numerator, we have derivative e to the x is e to the x. Derivative of 1 is 0. Derivative of x is 1. So we have e to the x minus 0 minus 1. In the denominator, we have the derivative of x e to the x there. So we're going to do product rule. It'd be the first times the derivative of the second minus the second times the derivative of the first. So that's going to give me x e to the x minus e to the x times 1. Okay, so we have x e to the x minus e to the x. So that we're going to put that down here. We have x e to the x minus e to the x. I don't know why I put a parentheses there, so let me do that here. Let me write that here. So I'm going to have x e to the x minus e to the x. And then remember, we've still got this minus 1 here. When I take that minus x, when I take that derivative, I get minus 1. Okay, so now we check this here by direct substitution. We're going to get e to the 0 minus 0 minus 1 over 0 e to the 0 minus e to the 0 minus 1. And e to the 0 is equal to 1, so we get 1 minus 1 over sorry, this was a plus there because of the product rule. So I'm going to get 0 plus 1 minus 1. So I get 0 over 0. So I have 0 over 0. And what is that? That's an indeterminate form again. All right, but that's no problem because we just do L'Hopital's rule again. So use L'Hopital's rule again. And so now we have the limit as x goes to 0. We're going to take the derivative of e to the x minus 1 over the derivative of e to the x e to the x plus e to the x minus 1. And that's going to give me the limit as x goes to 0 of e to the x in the numerator. And in the denominator, we can use the fact that the derivative of x e to the x right here, we saw that that equaled this. So we're going to just put that down there. We're going to get x e to the x plus e to the x. And then we have the derivative of e to the x. So that's going to be e to the x. And then we have minus 1, derivative of that is 0. Okay, so then we do direct substitution. And when I do that here, I guess I don't need to write that. So I'm doing the direct substitution here. I'm going to have e to the 0 over 0 e to the 0 plus e to the 0 plus e to the 0. And that's going to be 1 over 0 plus 1, which is 1/2. And that's my answer there. Some of you may say, well, when I was at this stage that I'm going to circle in blue, could I factor out an e to the x in the top and the bottom? Yes, you could do that. If you wanted to, you could also go here and you could factor out an e to the x in the top. And in the bottom, when you factor out e to the x, you have x plus 1 here. And then the e to the x's cancel out. So then you have the limit as x goes to 0 from the right of 1 over x plus 1. You substitute in the 0 there, then you get 0 plus 1 plus 1 over the quantity 0 plus 1, which is going to be 1/2, and you get the same answer. So either way works. Which way is better? Really, I can't say which way is better. I think they both work, but they both get you the same answer, so that's great. All right, hope that helps. Have a great day.